What about absolute value equations? How do we solve those? Absolute value equations and inequalities. Well, what does the absolute value do? It takes a negative value and makes it positive. We denote the absolute value as whatever expression or value is in between these two vertical bars. If the value of x is positive, it stays positive. If it's negative, the absolute value makes it positive. So that means the absolute value of 2 in this case would equal 2. That's one solution. X equals 2. But also, the absolute value of negative 2, the absolute value turns that positive to make it also equal 2. So another solution is x equals negative 2. Note, I always have a positive and a negative solution case for the absolute value. So, okay, what if x is a more complicated expression? Who says it has to be just simply one variable? What if I said absolute value, instead of just x minus 5 equals 2? How would we go about solving that? Well, again, we know x minus 5 could evaluate to the positive 2. So we set up our positive case solution. And by the way, we also know x minus 5 could equal the opposite of 2 in the absolute value, in which case our equation is also true because the negative 2 is converted to plus 2 in the absolute value symbols. So we have a positive and a negative case solution for every absolute value equation, right? We don't have an easy inverse like addition, subtraction, multiplication, division, or for positive values of x, taking the square root of the square, vice versa. We have to adjust for this positive and negative case. That's how we go about solving absolute values. So now I've removed the absolute value symbol by setting up the positive negative case, and that's the key. Now I can solve. Add 5 to both sides on the first one, and x equals 7. On the next one, add 5 to both sides again, and x equals minus 2 plus 5, which is 3. And those are the solutions to our absolute value equation. We set up our positive and negative case and solve. So that's how we would approach it algebraically. Many of you might have learned or say absolute value is a representation of distance, and it is. If we think about it, the distance between any 2 points on a number line, say my solution x and 5, the point 5 on the number line, we represent that distance as x minus 5. This absolute value equation is saying that distance is a distance of 2. So my solution point x is a distance of 2 from 5. Well, we know that's x equals 7. But also 2 in this direction, which would be 3. That's also a distance of 2 from 5. And in that case, I might get a negative result, but the absolute value of x minus 5 makes it a positive distance, and x equals 3 is also a solution. Note, I have the same solution points, but I'm interpreting my absolute value equation as a distance here. It's a distance that's 2 away from 5. This intuitive approach can help you quickly discern the solution points of an absolute value equation without having to use the algebra. But I caution you to be careful. As this equation gets a little more complex, it becomes more and more difficult very quickly to sort of intuitively interpret the absolute value as a distance function for most students. When solving absolute value equations, there are a couple important points that students should take notice of. For example, number 1, 2x plus 10 absolute value equals negative 5. What do we think of that? Well, right away, if you're attentive, that cannot be true. The absolute value is always positive. It takes a negative, makes it a positive, and keeps a positive positive. There is no way a positive can equal a negative value. So right away, we know that case would have no solutions. Secondly, what if I had minus 2 times absolute value x minus 5 plus 10 equals 20? A lot of students might try to jump right into the algebra and take a positive case and a negative case right here. They'll say minus 2 times x minus 5 plus 10 equals 20 and try to solve that. And then in the negative case, minus 2 times x minus 5 plus 10 equals negative 20. Be careful about that. The change in the positive and negative case does not apply to the other parts of the equation beyond the absolute value. So we can't be certain this is going to be correct. The correct approach should be to isolate the function, the absolute value function, and then apply your inverse operation, in the case of absolute value, a positive and negative solution case. So isolate your function first. As a general rule, whether your function is a square function, a trig function, any other type of function, you probably want to isolate that function first and then try to undo it to then solve for the variable. So how would we work that in this case? First things first, I would subtract 10 from both sides. And that would give me minus 2 times the absolute value x minus 5 equals 10. And then I'm going to divide through by negative 2 on both sides. And that isolates my absolute value expression on the left side. That equals negative 5. Well, right away I see again, just as we saw above, this will not work. It'll have no solutions. But the important point is here, only at this point when I've isolated absolute value by itself on one side can I apply my positive and negative case solution. Don't try to do it when other things are going on with the expression. What about absolute value inequalities? In this case, absolute value of x is less than 2. How does that work? Well, again, that means x, if we go with our positive and negative cases again, it means x is less than 2. It also means the x is less than the opposite of 2, but again, wait a second, if we're changing on an inequality the sign for our negative case, we have to switch the direction of our inequality. X is greater than negative 2. Absolute value inequalities are essentially the same as compound inequalities. So in this case, x is less than 2 and greater than negative 2. This is an AND condition. When my absolute value is less than, it's effectively an AND condition. And I could graph that as such. That gives us our typical at 2 and negative 2, our typical barbell type solution in between the 2 points. About x minus 5 is less than 2. Before we saw with the equations, I can interpret as a distance. Can I interpret this as a distance? Yeah, my solution, the distance between x and 5, because that distance is represented as x minus 5, the absolute value means it's in both directions, must be less than a distance of 2. So that means right away I can say from my center point of 5, I can go up to 2 to the right, but not 2 or further, and I can go down 2 to the left from 5, but not down 2 or further. So my solution right away, I can kind of eyeball this as a distance and interpret it as x is less than 7 and x is greater than 3. Again, I'm using the same distance interpretation I did on my absolute value equations. Let's solve algebraically my positive and negative case here. What do we get? X minus 5 is less than 2. That's my positive case. Pretty simple. I usually just take away the absolute value symbols. By the way, don't leave your absolute value symbols there for your positive and negative case. A lot of students do that. The whole point of generating a positive and negative case is to undo the absolute value function. Okay? Now, here's a very important point. If you didn't see it from the first example, on inequalities, my negative case must correspond to a change in the direction of my inequality symbol, as we learned when we multiply and divide through by negatives on inequalities. So in this case, x minus 5 is not less than negative 2. It becomes greater than negative 2. I've switched the direction of my inequality symbol. And by the way, I can write this again as a compound inequality here. X minus 5 is less than 2 and greater than negative 2. And I could solve it with that three-way inequality if I chose to. I'd add 5 to both sides. I get x is less than 2 plus 5, or 7, and x is greater than minus 2 plus 5, which is 3. Exactly what I expected from my intuitive interpretation as a distance. If you aren't comfortable with interpreting inequalities or absolute value inequalities as distance, don't worry about it too much. Just remember, you can always solve algebraically with your positive and negative case. Note, in our first two cases, the absolute value inequality was less than 2, or the fixed amount. That resulted in essentially a distance interpretation of my center point. All solutions were within some distance of that center point, which resulted in a compound inequality, which essentially put x in between two values like that. And the graph, as a result, was our standard barbell graph, where we had 2 points, and the intersection of inequalities between those 2 points was the solution set. And recall, that was our AND condition at play. But what happens if our inequality is greater than, or the absolute value is greater than the value? Say, absolute value of x minus 5 is greater than 2. How would we solve that? Well, on a distance interpretation, we'd interpret our solution as a distance greater than some amount away from a center point. In this case, greater than 2 away from 5, which would probably be x is greater than 7 and x is less than 3. Algebraically, we could go through and solve that and see if that's in fact the case. Let's try our positive and negative solution cases. That's x minus 5 is greater than 2 in this case, and x minus 5 is less than negative 2. So that means x is greater than 7, x is less than 3. Well, what exactly is that? We can't write that as a three-way inequality like our AND condition. Why? Because this is an OR condition. Think about the graph. This is our case where the solutions greater than some midpoint, 5, 2 greater away to the upside. That's 7, or not including 7, but greater than 7, so everything to the right is 7, and greater than a distance of 2 down from 5, which would be 3, everything less than 3. This was our OR condition. In other words, a point in the solution set here cannot also or and be in the solution set up here. It's one or the other. So the only way to make it true, a true statement, is with our OR condition. So notice the difference in graphs from the different inequality setups on absolute value inequalities. They do correspond to our compound inequalities, as we saw in the earlier lesson, but they're different. And again, you can recognize them as different cases with the less than and greater than symbols.